the next concept we have to discuss from module 1 is memory map. Okay, so let's start with memory map. Memory map is what? Memory map is the organization of the computer's memory into different sections. So it shows how memory is arranged and how different parts are basically used. So like you're organizing the computer's memory into different sections. That is what actually memory map means. How the computer's memory is basically organized into different sections is shown by memory map. And how memory is arranged, how different parts are basically used. Okay, that is what the memory map is there. So in memory map you have to understand the definition of memory map. What is the definition of the memory map? A memory map is the organization of the computer's memory into different section. Organization of the computer's memory into different section. It shows how the memory is arranged and how the different parts are used. That is what you have to understand. How different parts means which part is used for program instruction, which part is used for data, which part is used for stack, heap, and all. Okay, so it's like how the different parts are basically used and how the memory is arranged. That is what memory map gives, how memory is arranged and how different parts are used. So you can say that memory map is organization of the computer's memory into different sections. So it shows how the memory is basically arranged and how the different parts are used. That means it's like program instruction. Like you have to understand that each range is assigned for a specific purpose. For a specific purpose the memory is divided. So one range in the memory would be for program instruction, the next would be for data storage, next would be for stack and heap, and next would be for operating system, next would be for input output devices. So it helps the CPU access the data and devices correctly because we know the memory is divided. So that means each range would be for, some range would be for program instruction, then some for one part of this memory would be for the stack and heap, one part would be for data storage, one part would be for let's say for the input output devices, one part would be for the operating system. So that is how memory is divided. So we can easily access the memory, right, easily access the data and devices correctly because this is how the memory is basically divided into different sections. And so therefore memory map shows that how the different sections, how the memory is basically organized and how the different parts are basically used here. Understood? So here if you see, you have to understand this main thing, that is what are the different segments. Okay, there are mainly 5 parts or 5 segments in how the memory is basically divided. There are different segments and mainly you have 5 segments here: the test segment, the global data segment, the dynamic data segment, okay, and the stack segment is there, and the operating system OS, that is OS operating system, and IO segment, that is the 5th segment. So you have the text, the main text segment. Okay, now what does the text segment do? The test segment would store the program's instruction. What does the global data means? Stores the global data and static variables. Okay, what is dynamic data segment means? Stack and heap, mainly heap. Okay, segments for exception handlers is there, that is stack segment is also there, then exception handlers, then OS operating system, and IO devices, IO segment is. So these are the different segments. Okay, test, global, dynamic data segments, exception handlers, IO, OS segment is also there. Fine. Now we have to understand what are the different functions of the memory map. Memory map defines these functions: where the programs are basically loaded, where devices are loaded, where interprets are controlled, and how OS operating system manages the memory. So if in your exam, if the question is like, okay, what are the functions of the memory map, then you have to say this function. You can see where the program is there, where the program part, the text part is different place. So where the program is basically loaded, and we can say where devices are located. We have IO segment, so where devices are located, where interprets are controlled. Interpret controlling, there would be another segment. So where this interprets are controlled, how the OS is managing the memory. So these are the different functions which is done by the memory map. So where the program is loaded, where the interprets are handled, where how the OS manages the memory, right, and how the devices are located, where the devices are located, like where the programs, where the devices, where the interprets and local, how OS manages the memory. So the basic 4 important functions of the memory map. Okay, so we have said first what is the definition of the memory map. It is like the organization of the computer's memory into different sections. So it shows that how the memory is basically organized and how what each part basically does. So it can have program instruction part, the stack heap part, the IO part, the exception handler part, the memory OS part would be the data part would be the global data part, right? So we told them mainly 5 segments are there: the text segment part, the global data part, the dynamic part, data segment part, exception handler, OS or IO part, right? Then we talk about the main functions of this memory map, like it tells us where the program is basically there, where the program is basically loaded, I would say, where the interpret can occur, where the devices are located, right, where the devices basically are located, and how OS manages the memory. All these things would be there. Okay, so this is the main thing that you have to understand mainly. Then there is one diagram, that is this diagram you have to understand. That is the example of this RISC-V memory map. In RISC-V, this is how the memory map looks like. Okay, this is RISC-V memory map. Okay, so here if you see, this is the high address, high address, and we are going to the low address here. So first we have the operating system and IO, which is at the high address. Okay, then we have the stack and heap part, and the space between them for growing, shrinking part and for stack and heap. Then global data part, text part, and last we have the exception handlers. Fine, so you have to learn this diagram. This is how the memory is organized in our RISC-V processor. Understood? So you have to learn what this particular example of this RISC-V memory map you have to learn. Okay, here high address you have the IO device, operating system. Then you have the stack, then there's some space for the heap part, stack part is also there. Then you have the global data part. Fine, then you have the global data part, text, and last we have the exception handler. So you have to see that there are some pointers. For stack you have SP pointer, for global data you have global pointer, and for exception handlers, text handler, program counters, PC pointers are there. So while you are drawing this image, you have to mark these address. I would say just mark that this would be the high address. Okay, this is the lowest address, that is enough. Then this is how the memory can be divided. You have the stack pointer, SP pointer, global pointer, and the program counter point would be the fine. So you should learn to draw this diagram. That is one important thing that I want to tell. So here we have to discuss each of this segment. The text segment is here, the global data segment is the dynamic data segment is the in this middle part for stack and heap, right? Then we have the exception handler, OS and IO segments. Exception handler is at the last. IO and OS segment is at the top, at the high address part. So you have to learn each of them. Okay, so first let's talk about the text segment. Text segment is the code segment. Okay, text segment stores the machine language user program. Okay, that means it stores the program's instruction. It stores the program instruction, machine language program instruction, we can say. In addition to code, it also includes the constants and read-only data. Addition to the code, mainly the text segment I told you, we have to understand mainly the text segment. What does it stores? What does the text segment mainly stores? Okay, that is one important thing. Right, that is one important thing. Mainly I told you it would store the what? Code. 1 minute. I'm not able to write here. Okay, it mainly stores the code. Okay, but I told you it can also store this machine language. That is, it is mainly stored in the machine language program instructions. Okay, then it can also store, on other hand, the literal constants and read-only data. It can also store that also, the text segment. Okay, then you have the global data segment. This global data segment is storing the global variables and static variables. Okay, these variables are accessible. Global and static variables, what is the main main important thing about this global and static variable other is that they can be accessible to all the functions. That is, it exists throughout the program execution. Okay, that is, if you understand that, global data segment means what? They are storing the global and static variables. Global variable specialty is what? They can be accessed by all the functions in the program. So throughout the program execution, it basically exists there. Fine. The local variables, if you see, they are defined inside the function and can be, like, they are present inside the function and it is stored in stack or registers. Okay, within the function. But local variables are allocated before the program even begins. Okay, before the program execution starts, before that itself it is allocated, and you can access this using a global pointer register, that is GP. Okay, so these are the important things that you have to remember. The underlined part, that is global data segment, means it is like global data segments include the global variable as well as the static variables are there. These are all the global variables and static variable specialties that they are accessed by all the functions, right? They are accessed by all the functions and we are going to exist throughout the program execution. Local variables are the variables within the function which is there inside the function and it is stored in the stack or the, right, that's what it's called, stack or registers. Now global variables means they are allocated. These are basically allocated before the program even start its execution. So it is like using the global pointer you can basically access it. Okay, so this is the most important things that you have to remember about global data segment. Then we have the dynamic data segment. In the dynamic data segment, as you can see, it contains a heap, right, and it contains stack. So this is the main thing, it contains the heap and the stack. So you may think what it is. Now we know memory is allocated and deallocated dynamically here, and the data part is not fixed at the program start. It can change during the allocation. That means stack, a heap means what? Malloc. When I'm calling new space, I can allocate there some of the space. Growing part means what? Some of the space I can allocate, right? Some space I can allocate here. Stack, through the function call I can add more function call here. So what happened is that the more space is needed here. So during the runtime, it is basically this dynamic data would change. It is like, it is not fixed. The space is not fixed. Dynamic data can change. Okay, so here memory can be allocated and deallocated dynamically. That is why it is called as dynamic data section part. Memory is allocated and deallocated dynamically through the malloc function and through the function calls in the stack. That is what you have to understand. Okay, malloc, right? Through this malloc, basically this happens, right? This is what dynamic data segment. So dynamic data segment contains heap and stack, first point, and here memory is allocated dynamically and deallocated. Now how the memory is allocated dynamically and deallocated? Because of the heap. Because if I'm considering heap, heap means what? During the runtime itself, only during the execution time, we are adding more space to a variable. Let's say to x I am adding more using the malloc function. I will add more space dynamically. I am increasing the space for x. Now stack means what? When function calls and all come, you are going to push that to the stack. So stack size can grow, right? So that means the size is not fixed at the starting. It can change during the execution itself. That is what dynamic data segment means. Okay, then you have this exception handler. Exception handler is located at the lowest memory region. It is storing the exception handling routines and boot code. Okay, so exception handler, what it do is that it would be reserved for exception handlers, right? That is exception handler routine and boot code. And the next is that it is used when error or interpret occur. Whenever any error or any interpret occur, then we are going to use this exception handler. Now OS and IO segment is like it's the highest memory part. It is reserved for the operating system and memory mapped IO devices. This is important. Now OS and IO segment is basically reserved for whom? The OS and IO segment is mainly reserved for the operating system, okay, and memory mapped IO segments, IO devices. Fine. So in the memory map, these are the most important things that you have to understand in the memory map. First part is the definition. Memory map is organization of the computer's memory into different sections such that it basically shows how the memory is organized and what part handles what, right? Which part is used for what. That is the main definition here, right? One minute, guys. Okay, how different parts are basically used, how the memory is arranged, and how different parts are basically used. It includes the program instruction part, the IO devices, the OS, the data, global data part, the dynamic data part, all it includes, the stack, heap, and all of these things are included in the memory map, how the memory is basically divided. Then I told the main 5 part segments are there: the text segment, the exception handler segment, the OS IO segment, the stack heap segment, that is the dynamic data segment, right? Then we have the global data segment. The main function is that which tells us where the data is basically, program is basically loaded, where the interpret can happen, where the devices are located, and how the OS manages this memory. These are the main functions of the memory map. Okay, then I have to discuss this part, right? I didn't discuss this part. So I have this part to discuss. That is, there are different types of memory which is present in the memory itself: ROM, RAM, stack, heap, memory mapped IO, and OS area. First is OS area, which is used for operating system. Memory mapped IO is used for the hardware devices. Heap, I told you, dynamically allocating the memory using the malloc function. And for function call and local variable to store that, we have the stack. Then RAM. The RAM stores what? The program and data. Now what do ROM do? I told you exception handler bootload is stored. Right. Exception handler routines are there. These are stored in the ROM. Okay, bootloader and all is stored in the ROM. So these are ROM is the, RAM is the, stack is the, heap is there, memory mapped IO is there, and operating system is there. So what are the things that it do? I told you that in exception handler bootloader is there. Bootloader is coming from the ROM. RAM. Now I told you in the text segment we are storing the program's code. So that is present in the RAM part. Now stack is what I told you. Stack would store the function calls in return variables and return values. So that is there in the stack. Heap is dynamically allocating the memory, that is using the malloc function. So you have the heap there. This is also another memory. Then memory mapped IO is for the hardware devices. Then OS area is reserved for the operating system. Understood? Now the main diagram that you have to learn here is that first in the highest position we have the OS and the memory mapped operating system and the IO devices. Then we have the stack, dynamic data segment, heap is the SP pointer for the stack pointer, global data for the, you have GP pointer for the global data pointer. Now text part, then finally you have the exception handler, which is the lowest memory part. Then we were discussing about each of this. Test segments show the program instructions, the program's main code and all. That is the main mission code of the user. Okay, that is basically there. And in addition to that, constants and read-only data is also present in the text segment itself. Then we talk about global data segment. Global data means it involves the global variables and static variables, which is basically exists throughout the program, and it can be called by all the functions. But there is local variable which is present within the function, and that is stored in the stack or the registers. Fine. Then you have global variables. Global variables are those variables which I told, which can be accessed by anyone, which is present allocated before the program's execution itself even started. And you have the global pointer also for accessing that global data. We have the global to access the global variable, we have the global pointer GP. Then finally we are talking about dynamic data segment. Dynamic data segment means dynamically allocating and reallocating the memory using the malloc and the function call. Fine. Heap and stack is the main thing here. Then exception handler. Exception handlers are basically done how I told you, it is present in the lowest memory. It basically contains the two things I told you it basically contains. Exception handling routines are present, and also it contains, I told you, boot code also it present for starting the program. Now OS and IO segment, I told you next is OS and IO segment, which is responsible for having that operating system and memory mapped IO. Okay, these are the different segments. So these are the main things about memory map. Now we have to understand another important thing, which is the Indianness part. Okay, that is Indian part and all we have to understand. First of all, we have to understand this thing, that is memory location, address and operation. You have to understand that the memory consists of many millions of storage cells. Each can store only one bit. So data is stored usually accessed in n bit groups, which is called as word, where n is the word length. This we already know. I told you memory contains a lot of cells, okay, lot of storage cells, but each cell can store only one bit of data. But we know 1 bit means what? It represents what? 1 bit. I told you 1 bit can represent 0 or 1, which is very small. So when memory is memory, you have to understand the memory consists of lot of this storage cells, which is basically can store only 1 bit, like 0 or 1. So if I'm accessing that one cell, means it is very slow. So usually while you are accessing the data, you are going to access in group of n bits. Okay, group of n bits. That group of n bits I told you in the previous video, that is the word. The group of n bit I told you, it is a word. Now, how many number of bits are present in the word? That would be the word length. So you have to understand, in the memory, I am storing that in each of this you have n bits. Okay, it's like we are storing it in a group of n bits, and that n bits can give me the first word, and similarly some other n words can give me the second word. If I am having a 8-bit 8-bit processor, or a 36 or bit registers and all, 36 bits would be there in the place. Okay, if I'm having 32-bit register, if I'm using, let's say 32-bit processor I am using, then that n value is 32. That means each word contains 32 bits. Each word can be represented in 32 bits. Okay, so that is how you are going to store, how the memory is basically organized, the address, the operations and all we are going to understand here. Fine. So this slide I hope you have understood, that is, if n bits means what? The number of bits which is present in a single word. If your processor is a 32-bit, the number of bits in one word would be what? 32. Fine. Now here if you see the memory, I told you memory consists of millions of storage cells. Each of this can store only one bit of the information, that is 0 or 1, because a single bit actually represents, so see 0 or 1 only you can store, but I told you it is very small. Only a 0 1 means very small amount of instruction only you can handle it here. So mostly the bits are basically not handled individually. You're going to handle them in the group of fixed size. I told you. So the memory is organized in the form of group of n bits. Each group of n bit would be called as the word of information, and that n would be the word length, because the number of bits. So this is how the memory is basically organized. Then I told you modern computers, let's say here the word length can be typically 16 to 64 would be the word length in modern computers. So the word length of the computer is, if it is 32 bits, means a single word can store 32 bit signed number or 4 ASCII encoded characters. So if I'm saying that a computer can store 32 bit, means each word can be 32. Okay, that means each word can store 32 bit signed numbers, like here 1 2 3 4, like that signed numbers it can store, like 0 1 can represent 0 for now here you have to understand one thing, signed bit it is. If I am having number, let's say 12, I can represent this 12 in 32-bit format in signed bit. Understood? So it would start from, actually will be like 0 1 2 3, like that. As if it is 32 bit, the last one would be 31 bit 31, because we are starting from 0, B0 B1, like that. So it would either, if you are having 32 bit, then it can be represented in the form of a 32 bit signed numbers, okay, like this. And here the last would represent whether it is a positive number or a negative number. If this last bit is 0 means what? It is a positive number. And if the last bit is 1 means what? It is a negative number. So the last bit can represent whether it is a positive or whether it is a negative number. Understood? The last bit can basically understand that. Fine. Now next is the ASCII encoded characters. In the ASCII encoded character means you are having character, and each character has 8 bits. So mainly 4 bits of ASCII, 4 ASCII character only you can solve here. Either if it is 32-bit, either it can be in this format, or either it can be in 4 characters formats, and each character, ASCII character, has 8 bits needed. So how many ASCII character you can store in total? 4 characters only you can basically store in store. So 8 bits ASCII characters when you are storing, since total is 32-bit, and in each ASCII character requires 8 bit. So total you can store only what? 4 characters. 4 ASCII characters only you can store because of that. Fine. So this is how the main thing you have to understand. If you have a 32-bit word length, you can represent in integer format, signed integer format, or ASCII characters. 4 characters can store like this. Fine. Now this is another important thing that you have to understand. That is, accessing the memory to store or retrieve a single item of information, either a word or a byte, requires distinct names or address for each location. Each memory location must have a unique address so the CPU can find. If the address uses k bits, then the number of possible addresses is 2 raised to k, and the address start from 0 to 2 raised to k minus 1. The only important thing is this. That is, if I'm having k bits is my address, so that means the number of possible address would be that if it is k bit, the number of possible address is 2 raised to k, which can range from 0 to 2 raised to k minus 1. Okay, that is 2 raised to k addressable locations would be there, and the range would be from 0 to 2 raised to k minus 1. That means if I'm having my k is 2, k is 2 bit means 0, k is 2 bit means 2 raised to k means 2 raised to 2, that is 4. Okay, that is 4. So that means 4 location, total addressable location is 4, and the range can be what I told you. The range is 0 to 2 raised to k minus 1. That means 0 to 4 minus 1, that is 3. That would be its range. Okay. Now if it's 3 bits, address bits are 3 means what? My total addressable location is 2 raised to k, that is 2 raised to 3, that is 8. So the range would be 0 to 7. Fine. Like that is how you are going to calculate the total addressable location and the address range when the address bits are given. If the address is this much bits given, then you can write that, okay, using this. Fine. Now this is one important thing, that is, whenever you are solving some numerical question and all, you can get 1 byte means what? 1 byte includes 8 bits. This is one important thing that you have to understand. 1 byte is 8 bits. And 1 kilobyte means 2 raised to 10 bytes, that is 1024 bytes. 1 megabyte means 2 raised to 20 bytes, that is 1024 into 1024, because 2 raised to 10 means 1024. So 2 raised to 20 means it is 1024 into 1024. Gigabyte is 2 raised to 30, and terabyte is 2 raised to 40. So 1 byte is 8 bits. 1 kilobyte I can write in byte format is 2 raised to 10. 1 megabyte is 2 raised to 20. 1 gigabyte is 2 raised to 30. And 1 terabyte is 2 raised to 40. Fine, so you have to know this. This is very important. Now you have to talk about this byte addressability. Now byte addressability, and you have to learn about big endian and little endian. This is the most important thing, I would say, big endian and little endian assignments. So I will discuss that also. So it is impractical to assign distinct address to individual bit location. What happened? Individual bit location in the memory. So most practical assignment to have a successive addresses refer to a successive byte location in the memory is called as byte addressable memory. Words are said to be aligned in memory if they begin at a byte address that is a multiple of number of bytes in the word. That means if the word length is 16 bits, the successive words are located at address 0, 2, 4, 6, etc. And if the word length is 32 bits, then the successive address locations are this. That means byte addressability means what? Byte addressability means each byte in the memory has a unique address. If I'm addressing byte addressability, then each byte would have a unique address. So it is difficult to give address to every bit. So memory is divided into byte, that is 8 bits. So each byte can have an address like 0, 1, 2, 3. That means I'm talking about when I am addressing the memory in the bits, it is kind of difficult. So I can make it byte addressable. That means we know 1 byte means what? 8 bits. So in that group I can address. So 8-bit one group can be address 0. 8-bit another group can be address 1, like that. So byte addressability means each byte you can give a unique address like 0, 1, 2, 3 and all. Okay. So if a word is stored at address, there are multiple of the word side. For example, if I'm having a 16-bit word means what? 16-bit word means what? How can I convert the 16 bits to byte? We know 1 byte means what? It is 8. 1 bit. I'm talking about. 1 byte means 8 bits. So if I'm having 16 bits, then it means how many byte? That would be 16 divided by 8. That is what? 2 byte. So that means the successive word location would be starting from 0. Then after 2 byte only, 2. Then after 2 is 4. Then 4 plus 2, 6. Like that. Okay. And if I'm saying the word length is 32 means, if 32 bits means 32, 32 divided by 8 is what? 4. So first location is 0, then is 4, then 4 plus 4, 8, then is 8 plus 4, 12. Like that you're going to represent the addresses. See, byte addressability means you're representing the memory in the form of byte. That means 1 byte would have the address 0 and the second byte would have address 1. So if there is bits, we know 8-bit group would be 1 byte. That would be address 0. And another 8-bit group next to it would be having bit represent one other byte, that would be having address 1. So if I am saying my word length is 16-bit means I'm going to find how many bytes that would be. So that means 16 bits means 16 divided by 8, that is 2. So my address location would be 2 plus plus, like that, 0, 2, 4, 6, like that. Now if my word length is 32-bit means the successive word location would be what? 32 divided by 8. That would be what? 4. That is 0, 4, 8, 12, like that. Fine. Now to understand big endian and little endian, I'm just going to explain with just one example. Okay. Big endian means lower byte address are used for the most significant byte, and little endian means the lower byte address are used for the least significant byte. For example, if I am having this 1536, 5876, okay, so this is my lower address. Now the lower address contains the least significant digit, that is, lower address containing the most significant bit would be the big endian, and the lowest address containing the least significant bit would be the little endian. So whenever I have a byte addressing, let's say 1536, 5879, then in this side is the most significant bit and this side is the least significant bit. So whenever it is said for me to represent in big endian means this lowest address, that is, this is my lowest address. So this is my memory address 0, 1, 2, 3, n raised to minus 3 up to n address positions. Here 2 address positions are given. Now how can I represent this address in big endian and little endian means? Big endian means the most significant bit we will write it in the lower byte address, and the least significant bit we will write, least significant byte we will write in the lower byte address. So the most significant byte is 15. So 15 we will write it in the lower byte address in big endian. So 15, 36, 58, 79, like that it will go. And little means the least significant byte. Little means what? Least. Okay, so least significant byte, that is 79, we will write it in the least addressable byte, that is the, okay, we'll write it in the lower byte address. So here you write first 79, then 58, then 36, 15, the opposite. See, it's opposite. Fine. So most significant byte in the lower address byte is big endian, and the least significant byte in the lowest address is the little endian. Fine. This is how we are going to write the little endian and the big endian. So this is the same example you can see here. Big endian means 15, 36, 58, 70 in that order. Little endian means 79, 58, 36, 15, that order it will come. Fine. So at the end, last also, we have 15, 36, 58, 79 would come last. In here, in the last, first 79, 58, 36, 15 would come at the last. Understood? This is how big endian and little endian are basically given. So this is about memory map. Thank you.